This question is about weak acids. Table 5 shows the pH ranges of some indicators. Identify the indicator that is most suitable for the titration between propanoic acid, which is a weak acid. So our pH curve is going to start around about 2 to 3. It's going to have a little bit of a blip into the buffer region, and then it's going to go vertical. So this vertical region is going to be around about 6. And because sodium hydroxide is a strong acid, probably up to about 11. So which is our best indicator? The most suitable will be thymol blue because its range definitely will fall. We don't really know on this 6 whether we're still going around the corner or not. Thymol blue, it says the most suitable. Thymol blue is going to fall right in the middle of this range. So thymol blue is the most suitable. So dissociation constant for propanoic acid, when that dissociates, it becomes CH3, CH2, COO minus and H plus. So our top line is the concentration of the dissociated ions, CH3, CH2, COO minus, the propanoate ion and the hydrogen ion over the formula of the undissociated acid in square brackets to represent concentration. Calculate the pH of a 0.1 molar propanoic acid solution. Give your answer to 2 decimal places. So they've given us the pKa. So the first thing I'm going to do is find the Ka by doing 10 to the minus the pKa value. So that on your calculator you need to find where on your calculator you have the 10 to the button, or you can type in 10 to the and then use the little box and type in minus 4.87. You're going to get 1.35 times 10 to the minus 5 moles per decimeter cubed. Ka is units. So that's our Ka value. Now for a weak acid, we're assuming that the amount of H plus and the amount of propanoate ions are the same, so we can simplify it to H plus squared. And so if we want to find the pH, we need to rearrange to say H plus equals the square root of the Ka value, which is on my calculator, times by the propanoic acid concentration. So it's the square root of 1.35 times 10 to the minus 5 times 0.1. So square root 1.16 times 10 to the minus 3. And then we know that pH is the negative logarithm to the base 10 of the hydrogen ion concentration. So the number we've just worked out. So we're going to use the little negative that isn't a takeaway, the minus sign on your calculator. Press in the log. If your calculator requires you to put the base 10 in, you can. And then I'm going to put in answer, execute. I'm getting 2.94 to 2 decimal places because that's what they've asked for. 2.935 on the calculator, 2.94 to 2 decimal places. For butanoic acid, we've been given a new Ka value. 20 centimetres cubed of 0.1 molar sodium hydroxide are added to 25 centimetres cubed. So we've got an excess of weak acid being added, and we're adding a base. We're going to be creating a buffer here because we're adding excess weak acid. So we've got this butanoic acid, CH3, CH2, CH2, CaOH. We're adding OH minus to it, sodium hydroxide. We're making butanoate ions and water. So we started off with how many moles of butanoic acid. So let's do 25 times 10 to the minus 3 to get the centimetres cubed into decimeters cubed. So we're starting off with 2.5 times 10 to the minus 3 moles of butanoic acid. We're starting off with 2 times 10 to the minus 3 moles of sodium hydroxide and no salt at the beginning. Now we've used an excess of acid, so all of the sodium hydroxide gets used up. and some of the butanoic acid gets used up. And so we're left with 5 times 10 to the minus 4 moles of butanoic acid. We've created some salt from that mixture, 2 times 10 to the minus 3 moles of salt. Now, at this point, we would probably want to write an expression for the Ka of butanoic acid. So we've got butanoate ions when it dissociates, and hydrogen ions over butanoic acid. Now, because we're creating a buffer here, we can't cancel anybody, no two numbers are the same, and we're trying to find H+, so we can rearrange to say H+ equals Ka times the formula of butanoic acid divided by the formula of butanoate ions and we can put the numbers in. Now, we've got moles and these are concentrations, but something interesting happens if you watch. We've got the Ka is 1.51 times 10 to the minus 5. Our HA value is 5 times 10 to the minus 4. So even if I divided by the volume, which is 45 centimetres cubed now, and then on the bottom line I'm going to put the 2 times 10 to the minus 3, it's got the same volume. So the volumes are going to cancel, and I can calculate my H+ value on my calculator without the volumes. So I'm going to use my calculator, 1.51 times 10 to the minus 5 times 5 times 10 to the minus 4 divided by 2 times 10 to the minus 3. And I'm getting a hydrogen ion concentration of 3.775 times 10 to the minus 6. So then I can do pH is the negative logarithm to the base 10 of the hydrogen ion concentration. So I'm going to do that on my calculator. And my calculator is saying 5.42 to 2 decimal places. Then the question says, a student plans to titrate butanoic acid with ethylamine. Explain why this titration could not be done using an indicator. Well, so butanoic acid is a weak acid. Ethylamine is a weak base. So if we think about the curve for that, we end up with a weak acid, weak base. The pH change is too gradual. There is no region, there's no big vertical region of rapid pH change where the indicator would need to change colour. There's no vertical part to the curve.